let us look at one more example to understand the subset construction method. Consider this language consists of strings of this form: AB, A square, B square. When I say A square, B square, it is AA followed by BB, or it could be A square, B power 4, or AB cube, or A power 4, B square, and so on. It has at least one A and at least one B, and there is no relation between A and B because they are two different integers. So one can think of in a simplest finite automaton. So let me stay at Q0 and continue to read A. Because I should read at least one A, I ensure I read one A before I start reading B. Similarly, I start reading plenty of B's using this, but I should ensure I read at least one B before I accept. So this is precisely what we have. So using Q0, we read in some sense n-1 A's, and nth A is read using this. Similarly, using Q1, with this loop we read m-1 B's, with this we read the mth B. Now it is a function, so other entries, if there is a transition on B and there is a transition on A, and if there is a transition on A comma B, all of them we go to Q3, and at Q3 if we get AB we continue to stay at Q3. So now the function is well defined. Now let's start constructing an equivalent DFA. So the idea is this: the start state of DFA is precisely the start state of this, because it is subset construction. It is a set containing Q0. Now with respect to this, let's look at the definition for A and B, and as we get new subsets, we start operating A and B with respect to that state. Okay, so that's precisely the idea. Let's look at delta of Q0 comma A. Q0 comma A says Q0 comma Q1, which means we obtain a new subset. So on reading A, we go to a new subset Q0 comma Q1, and delta of Q0 comma B is Q3. So when we read a B, we go to a new state set containing Q3. Now with respect to this, A and B is defined. Let's look at this new state Q0 Q1. With respect to Q0 Q1, we need to define delta of Q0 Q1 comma A. Q0 comma A is Q0 Q1, and Q1 comma A is Q3, correct? So we get this new subset, which means on reading A, we obtain a new subset Q0, Q1, Q3. Fine. On the similar line, if we read a B with respect to this, Q0 comma B says Q3, Q1 comma B says Q1 and Q2, which means what? When we read a B, we get a new subset. For Q0 it is Q3, for Q1 it is Q1 and Q2, so we get Q1, Q2, Q3. Fine. Now with respect to this, A and B is defined. Let's look at Q3. For Q3, A is again Q3 and for B also it is Q3. Fine. So let's look at Q1, Q2, Q3. With respect to this, if we define A, where do we move to? So for Q1, A is Q3. For Q2, it is Q3. For Q3 also it is Q3. So we go to this state on reading A. What about B? For Q1, it is Q1, Q2. And for Q2, it is Q3. For Q3, it is Q3. So therefore, we continue to read B at the same state, Q1, Q2, Q3. Fine. Now let's look at this state, Q0, Q1, Q3. Now if we consider the state Q0, Q1, Q3, let's look at, if you simulate A on this, Q0, A says Q0, Q1, Q1, A says Q3, Q3, A says Q3, so which means we stay at the same state and continue to read any number of A's. Now what about B? Q0, B is Q3, Q1, B is Q1, Q2, and Q3, B is Q3. Therefore, when we read a B, we come to this state. Fine. And since Q2 being the final state in the given NFA, this would be our final state because it contains Q2 in it. Okay. Now you get to see that with respect to each subset, on reading a symbol from sigma, be it A or B, we move to exactly one state. Now if you want to read A followed by B, yes, or A followed by any number of B's, yes, or you want to read two A's and followed by at least one B, yes, or any number of A's followed by any number of B's, ensuring at least one B. And if you just need one A, we do this. Okay. And it is like A followed by any number of B's, it is this. Suppose you say at least two A's followed by any number of B's, then you take this branch. Now it clearly accepts A power m, okay, A power n, B power m, where n is at least 1 and m is at least 1. Fine. And with respect to each of them, we have clearly defined. And now the question is, this has got 5 states, and is this a minimum DFA? That's one question. Answer is no. You can come up with a minimum DFA having just 4 states. That's one. And for example, can we redesign this mission and on the similar line to this? For example, I can do the following. Q0, read the first A, simply shift this, and at Q1 you continue to read the remaining A's. Now read the first B, and at Q2 you read the remaining B's. Okay, now you may get a B here, and with respect to this AB is defined, with respect to this B is defined, with respect to this you may get A. So go to a state called Q3. With respect to this you define AB and stay here. So now with respect to this state AB is defined, with respect to this AB is defined, with respect to this AB is defined, with respect to this AB is defined. Now you clearly see that when you read a symbol A, you go to exactly one state. When you read a symbol A, you go to exactly one state. When you read a symbol B, you go to exactly one state. So simple fine tuning of this NFA, we obtain a DFA. In fact, this is minimum as well. Okay. So now, but this procedure guarantees you a DFA for any NFA. Often constructing NFA is a bit straightforward. There are case studies where constructing DFA is not straightforward, for which this method will be of use. But the point that I am trying to highlight is, using this procedure we obtain some DFA. It need not be minimum always. In some cases we may get. For example, here is a case study for which what we obtain is not a minimum DFA, but a simple fine tuning of this NFA itself gives you a minimum DFA. Okay. So now this tells you that given an NFA having say n states, now we keep exploring the subsets. So it may so happen that you may list all subsets, and in the process when you convert NFA to DFA, and NFA having n states, so in the process of listing all subsets, we may list maximum 2 power n states. Okay, so less than or equal to 2 power n states. But there are examples where you have n state NFA and you will obtain close to 2 power n states. And one can construct such examples, so which means the conversion is not a polynomial time algorithm. Polynomial in what? Polynomial in n. Because polynomial in n, number of states, and now when it goes to DFA it becomes 2 power n, which is exponential in n, which is the number of states. So that shows that what we do, as we see a new subset, we operate each symbol in sigma. Then when you operate a symbol from sigma, you may get a new subset. Again, with respect to that new subset, we operate A and B or A, B, C. So for every symbol in sigma input alphabet, we look at new transitions. There are examples where n state NFA gives you 2 power n state DFA, which means the conversion process is exponential in the time, in terms of the number of states. If there are n states, you get exponential number of states in the DFA. Therefore, the conversion algorithm runs in exponential time. Okay, so that's something one should note. But larger message is the following. For every NFA, there is an equivalent DFA. The class of languages accepted by non-deterministic finite automaton is same as the class of languages accepted by deterministic finite automaton. Every DFA is also an NFA. That is by definition. But for every NFA, there is an equivalent DFA that one can obtain through this procedure. And so that shows that you give me an NFA, I will give you an equivalent DFA. That shows that for every NFA there is an equivalent DFA. So the class of languages accepted by non-deterministic finite automaton is same as the class of languages accepted by deterministic finite automaton. Okay. So that's something one should remember. There are many other interesting things about finite automaton which we shall explore.